Hey class, this is Mr. Shu again, and I am once again not in class. Hopefully we will still have a productive day. I know what you're thinking. You're probably thinking, Mr. Shu, you always give us a hard time for missing class. You call us scrubs, but you're actually the scrub. And I just want to say I've never denied being a scrub. Um, so yeah, anyways. Um, The question that we're looking at today, you probably had 13 minutes to work on already. It is a probability question. I believe it's a binomial scenario, but I'm not quite sure yet because I haven't looked at the question closely enough. But we will take a look at it shortly. You'll be given the opportunity to watch me do the question, and then you will also be given an opportunity to score it against the answer rubric as well as against my question. So let's take a look at this question together. A charity fundraiser has a spin the pointer game that uses a spinner like the one illustrated in the figure below. A donation of $2 is required to play the game. For each $2 donation, a player spins the pointer once and receives the amount of money indicated in the sector where the pointer lands on the wheel. The spinner has an equal probability of landing in each of the 10 sectors. Let X represent the net contribution to the charity when one person plays the game once. Complete the table for the probability distribution of X. Okay. Alright, so this is the expected value for when... okay, so this is the expected value of the game. So in other words, what the probability distribution is like the amount of money that the charity is going to make for itself to donate to whatever it is that they're donating to. So the $2 is how much the charity makes, which means if the spinner lands on 0, then that means the charity game makes $2. So if that's the case, then we have 6 spaces, I believe, that would make the charity earn $2. So that's 0.6. And where the charity pays out $1, or in other words, the charity gains $1, right? Because the person pays $2 to play the game, would be 0.3. And then the charity loses big if it lands on the $10 one, which would be 0.8. And not sure what work needs to be shown here, but maybe I would say each space, each sector of spinner has equal chance of being selected. Yeah. I'm just always kind of wary about showing work because they sometimes get kind of picky about that. Alright, so question B. What is the expected net contribution to the charity for one play of the game? Okay, so this means I'm just looking for the expected value, so I just take the values up here and I multiply by their corresponding probabilities. I should probably put that in parentheses. And I should get the expected value. This is 1.2 plus 0.3 plus, wait a minute, negative 0.8. Sorry. Math is not always the best. And so when you put this together, you get about 70 cents. Okay? So 70 cents per play. Okay. Alright, so I believe that's good enough. Showed some work there. I'm saying what I'm saying. So the charity, part C, the charity would like to receive a net contribution of $500 from this game. What is the fewest number of times the game must be played for the expected value to be 500? Oh, okay. So this is just what? Because we know of the rules of transformations, right? We know that in order for the expected value to be 500, it would have to be multiplied by some sort of constant. So this is the expected value of one game, and it has to be multiplied by some constant in order for the expected value to be $500, right? And we want to know what that constant is, and that constant represents, what x represents is the number of games. Okay? And so, when I do this on my calculator, do 500 divided by 0.7, 714.286 is my number. But it can't be 714.286 because you can't play that many games, so it has to be 715 games in order for the expected value to be at least 500, because otherwise it doesn't work. Okay? And I don't think you need to show more than that. Okay. Based on last year's event, the charity anticipates that the spin the pointer game will be played 1,000 times. The charity would like to know the probability of obtaining a net contribution of at least $500 in 1,000 plays of the game. The mean and standard deviation of the net contribution to the charity in 1,000 plays of the game are 792.79 respectively. Use the normal distribution to approximate the probability that the charity would obtain a net contribution of at least $500 in 1,000 plays of the game. That's very interesting. They automatically tell you to use the normal distribution. And they tell you the mean and standard deviation of it. So I'm assuming that you don't even have to justify that this is a binomial scenario, which is kind of interesting. Actually, this has some stuff that we haven't learned yet. Not a big deal, because I actually don't think that that's, yeah, believe you have to use central limit theorem yet, but we haven't gotten to it. So I'm sorry, I picked a problem. I picked a problem that has stuff in it that we haven't learned yet. But I don't think you need to justify it. I'm pretty sure you don't. I think you just have to use the calculation. So the first thing that you should probably say is that this is a normal distribution with a mean of 792.79. Actually, I don't think that that's necessary, but you might as well write more rather than write less. And in this case, since they tell you the mean and standard deviation, you just have to use normal CDF. Just write that you use that on your calculator, or use it like this is the electronic function that you plugged into your calculator. normal CDF from, what is it, 500 to infinity. Or if you use the A84, it's 1e to the 99, right? Which represents infinity. $792.79. And you want to label this as your mean and standard deviation. And if we go to our calculator, let's see what we get. I'm hoping that you don't have to justify it. If it says justification, that would be kind of bad for us. So lower bound is 700, upper bound, oh wait, no. Lower bound is 500, upper bound is infinity, and my mean is 500, and my standard deviation is 92, I forgot, 79. And, wait a minute. Sorry, I must have made a mistake. So lower bound, I want to find out if it's, oh, I think I know what mistake I made. So 500 to infinity. And the mean is 700. I think I put 500. Pretty sure that's what I did wrong. And then, oh, come on. 700. And then 92. Oh, I'm sorry. 79. Ah, okay. That looks more like it. I put 500 in the last thing. I apologize. So this is 9844. So 9844. All right. So this is the probability. And I don't think I would need to write anything beyond that, hopefully. So let's take a look at the answer rubric to see how we did. Okay, so, oh, they have justification here. Oh, it sounds kind of like mine, right? I don't know if you need that or not. 70 cents, 7.15, and then, I knew it. Okay, so this last one talks about central limit theorem. Don't worry about that. Our probability is 0.9844. Okay, so shouldn't be that big of a deal. So yeah, anyway, sorry. I might have picked a question that required some knowledge that you don't have yet. But let's see if we have to justify. Let's see if I'm right. I'm pretty sure we don't need to. So section 1, it says, essentially correct if all three probabilities are filled in correctly in the table in part A, and the expected value is calculated correctly in part B with work shown. Okay, so we're okay even without the justification in part A. So if we look at this, right, expected value is calculated correctly, and the probabilities are filled in correctly. I don't think that this phrase is necessary, but I'm always wary about stuff like that. Okay, so let's continue. Section 2, essentially correct if the response addresses the following two components. Provides a solution based on a reasonable calculation, equation, or inequality from the answer given in part B, and clearly selects the next higher integer as the answer. Oh, okay, all right. Okay, so in other words, our numbers were correct, and then we have to round up, like I was saying earlier,